Dear students, now let us discuss about our third module, which is bounded operator and adjoint. In third module, which deals about bounded operators and adjoint. So in this chapter, first we introduce what's an inner product space. So I thought that you are so familiar with the inner product. So an inner product is nothing but a function which assigns a scalar inner product xy, means an inner product on x, an inner product on xy which assigns an inner product on x which assigns a scalar inner product xy for all x comma y following x. So having some properties, inner product x plus yz equals inner product xy plus inner product xz. Linearity of the first variable. Inner product xy plus h equals inner product xy plus inner product xh. Linearity to the second variable. Inner product kxy equals k into inner product xy. Inner product yx. Inner product yx is inner product xy bar. And inner product xy is always greater than or equal to 0. Also we know that inner product xx equals 0, that implies and is implied by x equals 0. Agreed. So these are some preliminary properties of inner product. So inner product is nothing but a function which assigns as inner product on a linear space x, or a space x is nothing but a function which assigns a scalar value inner product xy which has these following properties. Okay. So a space together with a specified inner product is said to be an inner product space. A complete inner product space is said to be a Hilbert space. We know that complete normed space is Banach space, and here complete inner product space is said to be a Hilbert space. Agreed. If x and y are some inner product spaces, then the inner product defined on x cross y, that is inner product x1, y1, x2, y2 is inner product x1 plus x2, inner product x1, x2 plus inner product y1, y2. Means inner product on x cross y. If x and y are any two spaces, then inner product on x cross y is defined as inner product x1, x2, y1, y2 equals inner product x1, x2 plus inner product y1, y2. So, an operator A on an inner product space x over k, an operator A, that is A is from where to where? A is from x to x. Then by an operator A on an inner product space x is over k, we mean a linear map, that is A from x to x. Then A is bounded. A is bounded. That means modulus of or norm AX less than or equals alpha norm x for some alpha greater than 0, and for all x following x. For all x following x for some alpha greater than 0. So an operator A defined on a non-linear spaces or defined on a space x is bounded only when norm AX less than or equals alpha norm x for all x following x, and for some alpha is positive. Now, a bounded operator is always uniformly continuous. Why? Bounded operator is always uniformly continuous means, why? Because suppose A is an operator from x to x. A is a linear operator from x to x. Suppose A is bounded. A is bounded means norm AX less than or equals alpha norm x. So, for all x comma y following x, what about norm AX minus AY? Norm AX minus AY equals norm AI of x minus y. Since A is a bounded operator, norm AX less than equals alpha norm x. So norm AX minus y less than or equals alpha into norm x minus y. So finally, norm ax minus ay less than or equals alpha into norm x minus y, then clearly the bounded operator is always uniformly continuous. Also, a is a linear operator from x to x. Now, what is norm ax? Norm ax is defined as supremum modulus of inner product ax y. Supremum modulus of inner product ax y for all y following x, x comma y following x with a norm y less than or equals 1. This is the norm ax. How to define norm ax? When a is a linear operator, when a is a bounded operator, then norm ax is supremum modulus of inner product ax y for all y following x with a norm y less than or equals 1. So that means modulus of inner product ax y. Modulus of inner product ax y, which is less than or equals norm ax into norm y. Norm ax into norm y for all y following x. Norm ax is supremum modulus of inner product ax y. So with a y following x with the norm y less than or equals 1. So from here, modulus of inner product ax y less than or equals norm ax into norm y for all y following x. So how to define norm a? According to this argument, norm ax is supremum modulus of inner product ax y for all y following x with the norm y less than or equals 1. Moreover, modulus of inner product ax y less than or equals norm ax into norm y. So from here, what is norm a? Norm a is defined as norm a equals supremum modulus of inner product ax y for all x comma y following x with a norm x less than or equals 1 and norm y less than or equals 1. So norm a is defined in terms of supremum of modulus of inner product ax y with a x comma y following x with a norm x and norm y less than or equals 1. Okay. So these are some preliminaries about this inner product spaces. Okay. Inner product is nothing but a function on a vector space x or a linear space x which assigns a scalar value inner product x y having some properties. It is bounded when norm ax less than equals alpha norm x. Bounded operator is always uniformly continuous. Moreover, norm ax is defined as in this way. Norm ax is supremum modulus of inner product x y with a y following x with a norm y less than or equals 1. So that means modulus of inner product x y less than or equals norm ax into norm y. Thus norm a is supremum modulus of inner product x y with x comma y following x with a norm x less than equals 1 and norm y less than or equals 1. Okay. Now let us discuss an important result. So the theorem. The theorem says that let H be a Hilbert space. Hilbert space means complete normal linear space. Complete inner product space. Complete normal linear space is a Banach space. H be a Hilbert space. H is a Hilbert space. Hilbert space means complete inner product space. Okay. A following BLH. H be a Hilbert space. A is in BLH. Then there exists a unique uniqueness is strictly preserved there. There exists a unique B following BLH such that inner product AXY equals inner product XBY. Inner product AXY equals inner product XBY for all x comma y following H. So when inner product xy is inner product xby, if it established, now we define the adjoint of this A. Here B is known as adjoint of A and is denoted as A star. So when this relation established, that is inner product xy equals inner product xby, then B is nothing but the adjoint of A. So how to establish this relation? H is a Hilbert space, it's a complete term inner product space. then A fall in BLH. So its proof is for all x comma y fall in H. Consider Fy, define F restricted by Fy from H to K. Define a linear function Fy from H to K by such that Fy of x. Fy of x equals inner product Axy. Why? Because we define what is inner product. Inner product is nothing but a function which assign a scalar value having some properties. So here Fy from H to K is nothing but a function, okay, which is defined as Fy of x equals inner product Axy for all y fall in H. Enough. So inner product Xy for all x comma y fall in H. So what is Fy linear? Sure. Why? Fy of x1 plus x2 is inner product Ax1 plus x2 of y. Since inner product is linear, the linearity of inner product is already preserved. So what is Fy of kx1 or alpha x plus beta? Fy of alpha x plus beta is inner product A alpha x plus beta y equals inner product A alpha x y A alpha x y plus inner product A alpha x of inner product alpha x plus y. So it is inner product A alpha x plus beta. We have simply Fy of Fy of x1 plus x2 simply. Fy of x1 plus x2 is inner product A x1 plus x2y equals inner product Ax1y plus inner product Ax2y equals it is Fy of x1 plus Fy of x2. Clearly, it is linear with respect to addition. Moreover, Fy of k of x1, kx equals inner product A of kxy equals k into inner product Axy. Since it is linear, inner product is linear, that is k into Fy of x. So clearly, the defined function Fy, we define Fy from H to K with Fy of x equals inner product Xy, then Fy of Fy is always a linear function. Fy is linear function. Why? Because inner product is linear. Now, what is modulus of Fyx? Modulus of Fyx equals modulus of inner product Xy. But modulus of inner product Xy less than or equals norm X into norm Y. Okay, norm X into norm Y. That is norm X, but norm X less than or equals norm A. So norm A into norm Y into norm X. Okay, norm A is norm A into norm X. So it is norm A into norm Y into norm X. That means norm or modulus of Fy less than or equals norm A. That is norm or modulus of Fy less than or equals norm A into norm Y for all y fall in H with norm Y less than or equals 1 or mod Fy less than or equals norm A into norm Y. Clear? That means norm A is bounded. A is a bounded linear operator. A is in BLH. So A is bounded. So clearly mod of y less than or equals norm A into norm Y means Fy is bounded. Fy is bounded. Then that implies Fy is continuous. Fy is continuous. Now by the Rees representation theorem. The Rees representation theorem that's familiar with you. That states that the theorem states let H be a Hilbert space. H be a Hilbert space. F fall in H dash. Then there exists a unique Y fall in H. Y is unique. Unique Y fall in H such that F of x equals inner product xy. So Y be the representative of F. That is Rees representation theorem. If H be a Hilbert space, F fall in H dash, then there exists a unique Y fall in H with a f of x equals inner product x y for all x fall in H. Then this Y is said to be the representative of F in H. So here, Fy is continuous. Since Fy is continuous, then by Rees representation theorem, there exists unique set fall in H. Set fall in H such that Fy of x equals inner product x for all x fall in H by Rees representation theorem. There exists a unique set fall in H with a Fy of x equals inner product x set, where set be the representative of Fy. Agreed? So now define B of y equals set. By equals set. So since y set be the representative of y, so B is a By equals set, there B is an operator on H. Since B is an operator on H, then mod By or non By equals norm set. So norm set, there exists a unique set fall in H, Fy of x equals norm inner product x set, such that norm Fy equals norm set. Okay, here such that norm Y equals norm F. Now, so norm Fy equals norm set. So norm set equals norm Fy. What is Fy? Norm Fy equals norm mod norm. What is norm Fy? Norm Fy or mod Fy less than or equals norm A into norm Y. So which is less than or equals norm A into norm Y. Okay. That means norm By less than or equals norm A into norm Y. That means norm B less than or equals norm A. But A is a bounded linear operator. Therefore B is bounded. Since B is bounded, surely B is continuous. Okay. B is continuous. That means for all x comma y fall in H, modulus of our inner product AXY, what is inner product AXY? That is Fy of x. But Fy of x, what is Fy of x? Inner product XH. Fy of x is inner product XH, so it is inner product XH. But what is H? Set is By, that is inner product X By. So that means inner product AXY equals inner product X By. So our relation is established for all x comma y fall in H. Inner product AXY equals inner product X By. So listen, this B is known as the adjoint of A, and which is denoted as B is the adjoint of A, and the adjoint of A is denoted as A star. This is denoted as A star. A star is the adjoint of A. Inner product AXY is inner product X By, means inner product AXY equals inner product X A star Y. Inner product AXY equals inner product X A star Y, where A star is known as the adjoint of A. Clear? Now, our first part is finished. Now to prove the uniqueness of this B. There exists a unique B fall in H. How to preserve this uniqueness? How to establish the uniqueness of B? If possible, suppose inner product X or inner product AXY. If possible, inner product AXY equals inner product X By. If possible, there exists some B1 fall in BLH such that inner product AXY equals inner product X By equals inner product X B1Y. If possible, there exists some B1 fall in BLH such that inner product AXY equals inner product X By equals inner product X B1Y. So in order to show the uniqueness of B, we have to show that B equals B1. So consider this right side equality. inner product x by is inner product x b1 by. That means inner product x b1 minus b of y or b minus b1 of y equals 0. Since x is in x fall in h, so clearly x is for a non-zero x. This should implies b1 minus b equals 0, means b1 equals b. Therefore, the uniqueness is established. Okay. So this theorem states that, or that establishes the adjoint of a bounded linear operator A, which is known as, or which is denoted as A star, and the relation is inner product AXY is nothing but if A star be the adjoint of A, then inner product AXY equals inner product X A star Y. Okay, clear? Now let us consider another important result. Let H be a Hilbert space. Let H be a Hilbert space. Consider A and B fall in BLH. A and B fall in BLH. K is any scalar, non-zero scalar. K is any scalar. Then A plus B star. First you consider A plus B star. A plus B star means adjoint of A plus B is adjoint A plus adjoint B. A plus B star equals A star plus B star. How to prove this one? So for A plus B star equals A star plus B star for all x comma y fall in H. Proof is for all x comma y fall in H, consider inner product x A plus B star y. Inner product x A plus B star y. So which equals, since A and B are in BLH, A star and B star are the respective adjoints, then inner product x A plus B star of y equals inner product A plus B of x y. Since inner product is linear, it is inner product Ax plus Bxy equals inner product Axy plus inner product Bxy, linearity to the first variable. Since A star be the adjoint of A, it is inner product x A star y plus inner product x